200 gallons per second. That is how much water is leaking through the foundation of a dam in northern Iraq right now. Not over it, not around it, through it. Enough to fill an Olympic swimming pool every single hour, and it has been doing that non-stop for 40 years. The dam sitting on top of that leak is Mosul Dam, the largest dam in Iraq, 371 feet tall and 2.1 miles long, holding back 11.1 billion cubic meters of water above a city of 1.7 million people. If the foundation gives way, the United Nations estimates a wall of water 150 feet high would slam into the city of Mosul within 2 hours. No warning siren gives you enough time for that. The flood would keep moving downstream, hitting Tikrit within a day, reaching Baghdad, a city of nearly 9 million people, within 3.5 days. Between 500,000 and 1.47 million people live directly in the projected flood path. And here is the part that makes this different from every other aging dam story in the world. The engineers who built Mosul Dam knew the ground was bad before they ever poured the first load of earth. They knew the bedrock was made of gypsum, a soft mineral that dissolves in water the way sugar dissolves in tea. They built on it anyway. And ever since the reservoir filled in 1986, crews have been working around the clock, every single day, pumping cement into the ground beneath the dam to fill the holes that the water keeps eating. 95,000 tons of cement since opening day. That is not maintenance, that is life support. And the day it stops, the clock starts. To understand what is really going on beneath Mosul Dam, you have to start with the rock. Most dams in the world sit on granite or basalt or hard sandstone, rock that water runs over without doing much of anything. Mosul Dam sits on the Fatha Formation, a geologic layer made up of alternating beds of gypsums, anhydrite, marl, and limestone stacked in repeating cycles going down more than 300 meters the dam. Gypsum is not rare. It is the main ingredient in drywall, in plaster, in blackboard chalk. What makes it dangerous as a foundation for a dam is one simple property. It dissolves in water. Limestone caves like Mammoth Cave in Kentucky or Carlsbad Caverns in New Mexico take millions of years to form because limestone dissolves slowly. Gypsum dissolves at a rate roughly 100 times faster. Put a massive reservoir of water on top of gypsum bedrock, and the water does not just sit there. It finds the cracks, pushes into the joints, and starts eating the rock from the inside out, opening channels, forming caverns, widening pathways that pull more water through, which dissolves more rock, which opens wider channels. It is a feedback loop with no off switch. And that is exactly what has been happening beneath Mosul Dam for 4 decades. Construction began on January 25, 1981, on the banks of the Tigris River in northern Iraq, about 60 kilometers northwest of the city of Mosul. The project was led by a German-Italian consortium, Hochtief and Rodeo, under contract from Saddam Hussein's Ministry of Irrigation during the Iran-Iraq War. The regime prioritized the dam as a symbol of national power, and there was another reason for the chosen location that had nothing to do with engineering. Saddam wanted a reservoir large enough to flood the Badouch area in Kurdistan, cutting off a region that had been a center of opposition movements against his government. The dam was designed as a multi-purpose project: irrigation, flood control, water supply, and hydroelectric power for northern Iraq. It cost roughly $1.5 billion and was finished by 1984, with the power station going live on July 7, 1986. The dam itself is a zoned earth-fill embankment with a central clay core. It stands 113 meters tall, with a crest length of 3.4 kilometers, a crest width of just 10 meters, and upstream rock facing. 4 Francis turbines in the main powerhouse produce 750 megawatts. A second smaller station adds another 62 megawatts from 4 Kaplan turbines. A third pumped storage station contributes 240 megawatts. Total installed capacity sits at just over 1,050 megawatts, enough to power a significant share of northern Iraq. But even before the reservoir began to fill, the warning signs were visible. During construction, workers hit cavities in the rock. Sinkholes appeared on the surface near the dam site. The designers knew the gypsum was going to be a problem, and they planned for it. They installed a blanket of bentonite clay lining part of the reservoir bottom to block water from seeping into the subsurface. They drilled a grout curtain, a wall of injected cement deep into the foundation, to cut off water pathways. And they built a grouting gallery, a reinforced concrete tunnel running along the center line of the dam at the point where the earth fill meets the bedrock. The gallery is 7.5 feet wide, 12 feet tall, and runs the full length of the dam. It was designed so that crews could drill down through the floor of the tunnel into the rock below and pump cement into whatever voids the water had opened. That gallery was not a backup plan. It was part of the original design. The engineers built a hospital inside the dam because they knew the patient would never leave, and the patient got sick immediately. Within a year of the reservoir filling in 1986, water began flowing through the foundation and out the downstream side. The seepage rate hit 800 liters per second. That is 200 gallons of water pushing through the rock beneath the dam every single second, dissolving gypsum as it moved. 6 springs appeared on the left bank at different levels. Water chemistry tests showed high sulfate concentrations, proof that the flow was actively dissolving the gypsum on its way through. The grouting program ramped up from day one. Crews worked inside that narrow gallery, drilling holes into the rock below, mixing cement, bentonite, and sand, and pumping it down into the voids. When one hole stopped taking grout, they moved to the next. When they finished a section, they started over, because the water had already begun dissolving the fresh grout. One of the lead engineers on the grouting crew described the work in plain terms. You drill down, you pump cement until the hole will not take any more, but that does not mean the void is gone. It means you cannot push any more into it from that angle. The rock around it is still dissolving. The water is still moving. You have not fixed the problem. You have slowed it down. And then sinkholes started appearing on the surface. In 1986, several appeared on the right bank, roughly 500 ft from the dam. Between 1992 and 1998, 4 sinkholes opened up in a straight line running parallel to the dam axis. In February 2002, a large one appeared 500 ft downstream of the dam toe on the left bank, 50 ft deep and 50 ft across. It showed up overnight. The dam staff filled it the next day with 1,200 cubic meters of soil. They lowered the reservoir, then raised it again. The sinkhole reopened. They filled it with another 2,000 cubic meters. They raised the reservoir again. It reopened again, needing another 1,000 cubic meters. The ground beneath the dam was swallowing everything they put into it. The sinkholes were surface evidence of what was happening underground, cavities forming and migrating closer to the dam with every passing year. And every sinkhole was a signal. The gypsum dissolution was not slowing down. It was spreading. By 2004, the U.S. Army Corps of Engineers began studying the dam in detail. Their findings were not gentle. The Corps described the dam's foundation as fundamentally flawed. One consulting group wrote that the decision to locate such a major dam on the rock mass at the Mosul Dam site was a critical error. The Corps labeled Mosul Dam the most dangerous dam in the world. That designation has never been withdrawn. If you are finding this useful, hit subscribe. I am Simon, and every week we break down the engineering, the geology, and the politics behind the infrastructure stories most people only see in a headline. Now, here is where the story takes a turn that nobody outside of Iraq expected. In mid-2014, fighters from the Islamic State swept across northern Iraq, seizing cities, military bases, and critical infrastructure. On August 7, 2014, several hundred fighters took control of Mosul Dam and its power station. For 8 days, the largest dam in Iraq, the dam that the U.S. Army Corps of Engineers had called the most dangerous in the world, was in the hands of a group that had no interest in maintaining it, and no one knew if they might try to destroy it. The grouting stopped, the cement shipments stopped, the workforce scattered. During the brief seizure, equipment was looted, machinery was damaged, and supplies were taken. On August 16th, Kurdish Peshmerga forces, backed by Iraqi troops and U.S. airstrikes, recaptured the dam. But the damage was done. Even after the dam was back in government hands, the surrounding territory was not secure. The cement factory that supplied the grouting operation sat in contested ground. Supply chains were broken. Workers had fled. The grouting program that had been running 24 hours a day, 7 days a week for nearly 30 years had been interrupted. Satellite radar measurements told the rest of the story. A research team using data from the Italian Cosmos SkyMed constellation and the European Sentinel-1A satellite published findings in scientific reports, showing that parts of the dam had been subsiding, sinking into the weakened ground below. Deformation was rapid from 2004 to 2010, slowed between 2012 and 2014 when grouting operations were at their steadiest, and then accelerated again after the 2014 seizure when the grouting stopped. The data was clear. When the cement flowed, the dam held. When the cement stopped, the dam sank. The race between dissolution and grouting was not theoretical, it was measurable from space. The international response came fast after the recapture, but not fast enough. In late February 2016, the U.S. Embassy in Baghdad issued a blunt warning. Mosul Dam faced a serious and unprecedented risk of catastrophic failure with little warning. President Barack Obama stated publicly that the destruction or failure of the dam could prove catastrophic for areas downstream. U.S. Ambassador to the United Nations, Samantha Power, posted that she had just left a chilling meeting about the dam and warned that the entire population of Baghdad could face the choice to flee or be stranded by floodwater. Lieutenant General Sean McFarland, the top U.S. general in Iraq, told reporters that when it goes, it is going to go fast, and that is bad. In March 2016, the Iraqi government signed a $296 million contract with the Italian engineering firm Trevi Group to carry out an emergency stabilization program. Italy deployed roughly 450 soldiers, including elite Bersaglieri infantry, to guard the dam site, while Trevi engineers worked. The security operation alone cost an estimated $50 million per year. Trevi brought in 92 heavy trucks, underground 3D mapping technology, and modern grouting equipment. Between 2016 and 2019, Trevi completed roughly 403,000 linear meters of grouted boreholes, pumping about 41,000 cubic meters of grout, equivalent to 26,700 tons of solid material, into the rock beneath the dam. The U.S. Army Corps of Engineers stood up its own Mosul Dam Task Force in September 2016. More than 85 American civilian and military personnel deployed to support the stabilization work. The engineering firm AECOM mobilized over 100 professionals, with 60 relocating to the dam site to provide 24-hour monitoring of drilling, grouting, and outlet tunnel repair. They installed over 700 instruments across the dam, more than 400 of them automated, feeding near real-time measurements to dam safety engineers who used the data to decide where to drill next. The monitoring included surveying the dam surface once per month across 400 fixed monuments, plus synthetic aperture radar capable of detecting millimeter-scale movement from one month to the next. Every borehole was tracked by a computerized system logging pressure, depth, mix design, flow rate, and quantity of grout injected. Every drill hole became a data point in a 3D model of the dam's dissolving foundation. Colonel Philip Sakris III, the USA's Mosul Dam Task Force commander, described the situation in a single sentence that tells you everything. Mosul Dam, he said, is effectively a construction project that never ends. And he was right, because in June 2019, the international mission wrapped up. The Americans went home, the Italians went home, Trevi packed its equipment, and the Iraqi Ministry of Water Resources took full control of the grouting operation. The handover was celebrated with a ceremony attended by the U.S. ambassador, the Italian ambassador, and the Iraqi Minister of Water Resources. Everyone agreed the dam was in better shape than it had been in years. The foundation had been stabilized, the monitoring systems were state-of-the-art. Iraqi technicians had been trained on the equipment, but the fundamental problem had not changed. The gypsum was still dissolving, the water was still flowing through the foundation, and the grouting still had to continue every single day, or the voids would reopen. The non-stop race between logistics and chemistry that had been running since 1986 was now entirely in Iraqi hands, and Iraq is a country that has struggled with budget shortfalls, political instability, and institutional corruption for decades. In 2024, contracted grouting workers at the dam went on strike over unpaid allowances. Dam administrators responded with threats of dismissal. Audits conducted before and after the ISIS period found that allocated funds for grouting and repairs had been siphoned away by corruption. Equipment procurement was delayed. The scope of remedial work was limited not by engineering knowledge but by governance failures. And behind all of this sits a second dam, or rather, the ghost of one. In 1988, 2 years after the seepage problems at Mosul Dam became undeniable, the Iraqi Ministry of Irrigation began construction on Badouch Dam, roughly 20 miles downstream. The idea was elegant and terrifying in equal measure. Since there was no permanent fix for Mosul Dam's dissolving foundation, they would build a second dam below it to catch the flood if the first one failed. Badouch Dam was designed to hold back the full volume of Mosul Dam's reservoir, 11.1 billion cubic meters, in a massive empty pool, just long enough to release it safely downstream. It was the world's first flood wave retention dam. No other dam in history had been designed solely to protect people from the failure of another dam. Construction started, and then the first Gulf War hit in 1991. The project was suspended with roughly 30 to 40% of the work complete. It has never been restarted. The half-built concrete sits in the valley, slowly weathering, 35 years into a pause that nobody has ended. And here is the twist that makes the Badouch story even harder. The geology at the Badouch Dam site is almost identical to the geology at Mosul Dam, the same gypsum beds, the same karst features, the same dissolution risk. If Badouch Dam were finished, it would likely need its own permanent grouting operation, a second patient in a second hospital, running on the same life support as the first. So what does the math actually show if the worst happens? In 1984, the Iraqi Ministry of Irrigation commissioned the Swiss Consultants Consortium to model a full dam breach. Their findings have been updated and expanded by multiple research teams since, including studies by Luleå University of Technology in Sweden, the European Commission, and researchers at Mosul University. The models largely agree. If Mosul Dam fails at full reservoir capacity, with the water surface at 330 meters above sea level, the breach would release a flood wave traveling downstream through the Tigris River Valley. The wave would hit the city of Mosul, 60 kilometers downstream, within roughly 1 hour and 40 minutes. By that point, the water in parts of the city would reach 25 min, roughly 80 ft. The ancient city of Nineveh, which sits on the east bank of the Tigris directly across from modern Mosul, would be inundated. 28 square miles of the city would be flooded. Within 22 hours, the wave would reach Tikrit, Saddam Hussein's hometown, with a wall of water still standing at roughly 50 ft. Within 3.5 days, the flood would reach Baghdad. The capital would see water heights of 8 min in some areas, around 26 ft, with more than 80 square miles of flooding around the city center. The cities of Beji and Samarra, sitting along the river between Tikrit and Baghdad, would be hit by 50-foot waves of their own. Every bridge, every water treatment plant, every power station along the Tigris between Mosul and Baghdad would be destroyed or submerged. The European Commission modeled a total of more than 6 million people affected, close to 1/6 of Iraq's entire population. The energy of the floodwater in Mosul during the breach event would carry a stream power between 3.3 and 12.39 megawatts, compared to the normal river power of less than 55 kilowatts. That is not a flood, that is a liquid earthquake. The US government took the threat seriously enough to prepare a detailed emergency overview. It warned that flooding south of Samarra would resemble the aftermath of Hurricane Katrina, with standing water covering much of Baghdad for weeks to months. As floodwaters receded, mud and waste-covered remnants of previous infrastructure would be left behind. Bodies, buildings, cars, unexploded ordnance, hazardous chemicals, and sewage all swept downstream and deposited across thousands of square kilometers. The overview stated plainly that between 500,000 and 1.47 million Iraqis residing along the Tigris in the highest risk areas probably would not survive the flood wave unless they evacuated beforehand. The majority of Baghdad's population would be adversely affected, experiencing displacement, health hazards, loss of mobility, and destruction of homes and services. And here is a detail that almost never shows up in the coverage. The Iraqi government has an early warning system for a dam breach, but the warning time for Mosul, the city closest to the dam, is less than 2 hours. In a city of 1.7 million people, with narrow streets, limited evacuation routes, and a population that has already survived years of conflict, 2 hours is not a plan, it is a hope. The U.S. overview noted that advanced preparation of the downstream population, including information on where to go and how to get there, would be essential. But decades of war, political instability, and displacement have left those downstream communities with limited capacity to prepare for an event this large. The Tigris River that runs through all of this is not just a water source. It is the spine of Iraqi civilization. The land between the Tigris and the Euphrates is Mesopotamia, the cradle of civilization, where the Sumerians built the first cities and the first written language more than 5,000 years ago. The river still feeds millions of acres of farmland. It still provides drinking water to most of Iraq's major cities, the marshlands of southern Iraq, one of the most important wetland ecosystems in the Middle East, depend on the Tigris for their survival. Mosul Dam sits upstream of all of it. Every city, every farm, every water treatment plant along the Tigris for hundreds of miles is downstream of a structure that the U.S. Army Corps of Engineers called the most dangerous dam in the world, and that has required non-stop cement injections to stay standing since the day it opened. The broader political picture only adds layers. Iraq's relationship with Turkey, which controls the headwaters of the Tigris through its own massive dam projects, affects how much water reaches Mosul Dam's reservoir. Drought years in southeastern Turkey mean lower reservoir levels, which reduces the hydraulic pressure on the foundation and buys time. Wet years push the reservoir higher, increase the pressure, and accelerate the dissolution. The Iraqi Ministry of Water Resources has recommended keeping the reservoir level at or below 319 men above sea level to limit that pressure. The normal operating level is 330 men. That 11 men gap between what the dam was designed to hold and what engineers feel safe holding is a measure of how little confidence remains in the foundation. Meanwhile, the proposed permanent fixes remain exactly that, proposed. One engineering concept calls for a deep slurry cutoff wall beneath the dam, a concrete barrier driven down through the gypsum to reach stable rock below. The estimated depth would be roughly 200 m, about 600 ft. A wall that deep has never been attempted beneath an existing dam anywhere in the world. The estimated cost sits around $3 billion. Special equipment would have to be designed and built from scratch just to attempt it. And even then, there is no guarantee it would work, because the gypsum extends in every direction, and cutting off one pathway may simply force the water to find another. Another concept is to finish Badouch Dam, but the geological problems at the Badouch site are the same as at Mosul, and the half-built structure has been sitting exposed to the elements for 35 years. Restarting would require a full reassessment, new foundation treatment, and billions more in investment. In a country dealing with reconstruction costs from decades of war, competing demands for infrastructure spending, and a government that struggles to pay dam workers on time, the money for either solution is nowhere in sight. And so the answer for now remains the same answer it has been since July 7, 1986. Keep pumping cement. Arabi grouting crews work inside that narrow gallery beneath the dam, day and night, drilling into rock that is dissolving beneath their feet, filling holes that the water will reopen, chasing a problem that moves faster than they can patch it. They have pumped over 95,000 tons of grouting material into the foundation in 40 years, and the seepage has not stopped. The voids have not stopped forming. The gypsum has not stopped dissolving. Nobody has found a way to make it stop. Colonel Sechrist's words hang over the whole story. Mosul Dam is a construction project that never ends. Nadir Al-Ansari, professor of water resources engineering at Luleå University and one of the leading researchers on Mosul Dam, put it more starkly. "There is no guarantee the dam will ever be safe," he said. "Studies done on the dam all show that its collapse is imminent. The word imminent does not mean tomorrow. It means the conditions for failure are present and growing, and the only thing standing between the dam and collapse is a grouting operation that depends on funding, political stability, trained labor, and a steady supply of cement, none of which Iraq has been able to guarantee for more than a few years at a time since the dam was built." So tonight, somewhere inside that 7.5 feet wide tunnel running through the base of Mosul Dam, a crew is drilling a hole into gypsum bedrock that is dissolving under the weight of 11 billion cubic meters of water. They are pumping cement into a void that they cannot see the bottom of. When the hole stops taking grout, they will pull the drill, move 3/5 to the left, and start again. 60 kilometers downstream, 1.7 million people in Mosul are going about their evening. 300 miles further, nearly 9 million people in Baghdad are doing the same. And every hour, another Olympic swimming pool's worth of water pushes through the foundation of the dam that sits between the reservoir and all of them. The cement is still flowing, the water is still flowing, and the race between the two has no finish line.